Okay, we might as well get started. Let me welcome you to this class on topics in reinforcement learning. I'm Dimitri Bertsekas, and I'll be teaching this class together with Dr. Yuchao Li, who's sitting right here. And I've given this class for 6 years now. This is the 7th year. Each time is different. There's a lot of material from previous classes, which you can find at this link here. In this particular class, in this semester, we're going to focus a little more on applications relative to previous classes, and you'll see what I mean by that. In this lecture, we are going to have an introduction to the field. In particular, we're going to look at the connections between reinforcement learning and some other fields, dynamic programming, decision and control. And so let me give you my outline. I'm going to start with AlphaZero, a phenomenal chess program that came out a few years ago and forms a paradigm for what we're going to be covering in this class. And we're going to look also at the components of AlphaZero, the offline training algorithm and the online play algorithm. And also in the context, we're going to review those in the context of other games, such as backgammon, and also topics like model predictive control. Then I'm going to talk about the history of the subject and some general concepts underlying. Then I'm going to focus on this course, its connections to various fields. And near the end of the class, we're also going to talk about what's expected of you, what the organizational details of the course are, and so on. Then we're going to take a break for 15 minutes. We're going to be doing that in every lecture. And Yuchao is going to take over and talk about some of the technical content of the course, in particular, exact dynamic programming. Dynamic programming is at the foundations of reinforcement learning. So we're going to cover dynamic programming and approximate dynamic programming as a way to get to hardcore reinforcement learning methodology. And in this lecture, we're going to focus on deterministic problems where there's no uncertainty. And we're going to give some examples of dynamic programming and how it works. We're going to have an example on finite state, finite state problem, representative of a combinatorial optimization with traveling salesman problem in particular. Another example having to do with next word prediction and ChatGPT. Then we're going to talk about problems with continuous state space and the methodology of model predictive control, which is a dominant design methodology for control systems. Then we're going to talk about approximations, what we approximate in dynamic programming. And finally, issues that are specific to how this course is going to be run. So let me go to AlphaZero and also another program, TD-Gammon, which came out 25 years ago or so from AlphaZero. AlphaZero created a lot of interest in 2017 when it came out because its play was so innovative and also so strong. It beat out all human competition, of course, and also all computer competition by far. And it played original chess, which created a lot of interest, and there was a lot of publicity, and people started refocusing artificial intelligence with renewed enthusiasm. Now, TD-Gammon involves the game of backgammon, which is also a board game involving 2 players, but it also has an element of chance, rolling the dice. And in this way, it's somewhat more difficult than AlphaZero, which does not involve, than chess, which does not involve any uncertainty. Now, an interesting thing is that these 2 programs are based on the same design principles. And both of them involve two algorithms. One is the offline training algorithm, whereby the program learns how to evaluate positions, board positions, and also how to select moves in response to different positions. And this offline training algorithm takes place before the program gets to play against an opponent or a human opponent or a computer opponent. It's done as a preliminary phase using a training methodology that involves neural networks. And the second algorithm in AlphaZero and TD-Gammon is the online play algorithm, which is quite different than the offline training algorithm. It is the algorithm that the computer uses to select moves against humans like you and me, and also other computer programs. And this involves multi-step look ahead and algorithms such as rollout and cost function approximation. This will involve, these are concepts that we're going to talk about quite a bit in this course. And the online play algorithm in particular has a lot of connection with dynamic programming, the fundamental method of policy iteration, while the offline training algorithm has a lot of connection with reinforcement learning type of methodology involving training of neural networks and the like. Now, what we will try to do in this class is understand this methodology so that we can extend it and make it to apply more generally in a very large set of fields. In particular, we're going to look at the problems in control system design and methodologies such as model predictive and adaptive control. We're going to look at large language contexts and discrete optimization, like combinatorial optimization, problems of scheduling, routing, and the like. All of these are connected. The core methodology is the same for all of those, and that's what we're going to try to emphasize in this course. Now let me look at the online play algorithm in AlphaZero. It involves multi-step look-ahead minimization and a position evaluation at the end of the look-ahead. In particular, there's a state here, and the state is the board position. The board position at which we as a player have to select a move. And in AlphaZero, this is done as follows. We generate all possible legal moves from that position, and then the opponent chooses a counter move, and this is repeated for several moves looking ahead, several stages. And at the end of this look-ahead tree, we have various positions, which we can evaluate by means of a position evaluator, which is the product of the offline training algorithm. So from the current position, multi-step look ahead, taking into account the opponent moves, and position evaluation at the end, which is obtained through offline training. And after we make this move, then the opponent makes another move, and we get to play again, and then we repeat this. We form the look-ahead tree, position evaluation at the end, and so on. So the move here that is being selected is obtained by starting from the end and backing up this computation to obtain the best legal move at the current position, which we play. Now, this is done with a form of dynamic programming, a simple form of dynamic programming, and it's quite intuitively well understood. So the online play algorithm uses the results of the offline training, which is the position evaluator. And this is an example of a fundamental reinforcement learning approach that we will use extensively in this course and applies very broadly. It's called approximation in value space. This is the value here at the end that we approximate. That's where the name comes from. Now, this figure here has strong similarities with model predictive control, which we abbreviate as MPC. As I said, model predictive control is a dominant design methodology in control systems. It's used in places like self-driving cars, many different contexts. And we're going to talk about applications of model predictive control quite a bit in this course. So model predictive control uses, again, multi-step look ahead with position evaluation at the end, but there are a few differences. In chess, the state space is discrete, it's finite. There are only a finite number of positions at every stage. On the other hand, in MPC, usually the state space is continuous, or perhaps a mixture of discrete and continuous. Another difference is that in chess, the look-ahead tree is usually pruned by pruning off some branches that do not look interesting so as to facilitate the computation going forward. And but we want to do this because we want to go very deeply into the future, like 20 moves ahead, 30 moves ahead. And if we were to consider all the legal moves in these 20 moves, the tree would grow enormously and it's computationally not feasible. On the other hand, in MPC, usually this look-ahead optimization is exact. And how exact it is makes a difference. And we're going to come to this point later. And finally, there's another difference between chess and ordinary control problems, like in MPC, namely that chess is a two-player game, whereas in control systems, usually there's only one player. This difference has to be clarified, and we're going to talk about it later, but think of chess against a fixed opponent. Okay, you know the opponent is fixed, cannot change its strategy in response to the play of AlphaZero. Then this makes chess a one-player game, and there's almost a one-to-one mapping between AlphaZero and model predictive control, modulo the differences that I've discussed here. Okay, so now let's go to the offline training algorithm in AlphaZero. It's an instance of what's called approximate policy iteration. Policy iteration is a fundamental algorithm in dynamic programming. But it uses training with data that's self-generated. In other words, the program gets to play against itself to generate data from which the training is done. Now, what the offline training algorithm here generates a sequence of players or policies. A policy, you can think of it as a lookup table. For any given chess position, the lookup table gives you the move to play. So that's the policy that AlphaZero uses. It starts from some policy. It evaluates this policy by generating data and recording when it was successful and when it was not successful. So it evaluates its play, and it uses this evaluation to do a policy improvement to obtain a better lookup table, a better policy, which is stored in a policy network, a neural network that provides this lookup table, basically, encodes this lookup table. So this is used to this is used for another cycle of evaluation, policy improvement. So starting with a policy, we evaluate, we improve it, then we evaluate the improved policy, obtain a second improved policy, and so on. And hopefully, and indeed in practice, this happens to a certain extent, we get a sequence of policies that's better and better. And from a low-ranking player, it becomes a medium-ranking player, and then a high-ranking player, and then a phenomenal player in the end. So that's what we do. The current player is evaluated by playing many games. Its evaluation function is represented by a value network through training. The improved player is represented again by a neural network, a policy network, through this training. And there are some special wrinkles on the way this improvement is done. In AlphaZero, it's done with a form of multi-step look-ahead minimization called Monte Carlo tree search. More on this later, but it's like look-ahead minimization, except it's a little approximate. And now the results of the offline training and the final player and are stored and are used for online play. So we first do offline training, obtain these neural networks, and then use them for online play. Now let's go to TD-Gammon. It's a board game involving rolling of dice. The state here is the current position, but also the current roll of the dice. TD-Gammon is similar. It obtains it uses multi-step look-ahead with position evaluation at the end. And at the given position, the given roll of the die, it looks at all legal moves to play, then takes into account the next roll of the die and the play of the opponent, and goes forward for a few steps in a similar way as AlphaZero. However, because the look-ahead tree of backgammon expands very quickly because of this roll of the dice, it can't look very far ahead. So what it does, it uses a look-ahead that's simplified by using some base player, some reasonably good player to look forward for a number of steps before using the position evaluation. This is called truncated rollout, and it involves, in TD-Gammon, involves Monte Carlo simulation to generate these trajectories and these positions at the end, and look ahead in a cheaper way than it would take to do a multi-step a long look-ahead minimization. So it generates for a look-ahead tree involving several moves. It simulates the base player for some more moves at the tree leaves. This is called rollout and truncated rollout if it's limited. We're going to talk about rollout algorithms quite a bit in this course. And the effect of future moves is approximated by using the terminal position evaluation. And then we back up the scores to the current position, select the best move, roll the dice, the opponent takes over, and so on. Now, this rollout idea, extending the look ahead economically, it will also play an important role in other contexts, and in particular in discrete optimization problems, like traveling salesman problems, like routing problems, scheduling problems, and so on. And the role of the base player is going to be taken over by a base heuristic, some heuristic algorithms to extend the look ahead. So if you look at the previous figure and this figure, TD-Gammon is more general than AlphaZero, you might say. Now here's some empirical observations using these programs. The first thing is that the AlphaZero online player plays much better than the offline trained player. The offline trained player uses zillions of processors, lots of training, huge amounts of data, and yet it is a mediocre player in chess terms. It's much worse than the phenomenal player that the online player is. The online play is a phenomenal chess player. This one, you can beat it yourself, actually. If you're even a medium strength player, you can beat it. So that's an important insight which holds in generality and on which we're going to focus. Namely, putting online play on top of offline training can gain you a great deal. Another insight is that the middle portion of TD-Gammon is very beneficial. In other words, TD-Gammon plays much better with truncated rollout than without rollout. Backgammon and the TD-Gammon program in particular had a long history. It was originally implemented in the late 80s using and trained using a method called supervised learning that we're not going to talk about here. It's not reinforcement learning, and the results were not very encouraging. It could play reasonable backgammon, but it was far from beating strong players. Then a few years later, TD-Gammon was implemented in this form here, but without the middle portion. And it came close to beating world champions. This is what I mean by online play on top of offline training. There was a huge improvement from the TD-Gammon of the late 80s to the TD-Gammon of 1993, let's say. In 1996, then this middle portion was implemented, and then TD-Gammon became unbeatable. It was playing almost perfect backgammon. It could beat any human. The only problem was that this simulation here was very time-consuming. So this player could not play in real time. Current implementations of TD-Gammon, which you can find on the internet, do not have a substantial middle portion here, and they will give you a pretty good game. But anyway, the important fact here is that this truncated rollout to extend the length of a look ahead can be very beneficial. Okay, so I think we stop right here. The fact that AlphaZero online player plays much better than the offline trained player, and also that in TD-Gammon, rollout makes a big difference. And in this course, we will aim for explanations, insights, and generalizations through abstract Bellman operators. There's something called a Bellman equation in dynamic programming. There's something called a Bellman operator there. And we're going to be using this concept quite a bit. We're going to explain what's happening by visualization. And there's a deep theoretical insight here, namely that approximation in value space, this principal method for reinforcement learning, is closely connected to Newton's method. Now, Newton's method is the one that you know and love from calculus. It's the same thing, and it's a little adapted to the context of dynamic programming, but the ideas are the same. Newton's method is extremely powerful in solving equations, in solving optimization problems, and this power is transferred within this framework. It explains why all this stuff holds. Now, we're not going to get to this until 2 lectures from now, and still we will not be dealing with abstract Bellman operators, Newton's method, and so on much in this course, but everything that we're going to cover is based on this foundation here. And those of you who are interested to dig in deeper, you can explore this further. Okay, so what's the framework of this course? We aim to unify several areas of large-scale computation. The first is reinforcement learning as practiced by the AI community. Then approximate dynamic programming as practiced by parts of the optimization and operations research community. Model predictive and adaptive control as practiced by the control systems community. All of these things are very closely connected. Now, discrete optimization like integer programming and algorithms that are popular in computer science. Parts of that methodology also is connected to what we're going to cover. And then parts of the emerging area of large language models is also connected with what we're going to talk about. And we're going to give, of course, examples of all this. Now, we're going to rely on dynamic programming, the theory of exact, approximate, and abstract dynamic programming. Dynamic programming is at the foundation of reinforcement learning. That's not going to change. That's the way it is. That's the mathematical foundation, and plus approximations and exact dynamic programming converted with that use of approximations is basically reinforcement learning. That's the way to view it. That's the way I view it, and that's the view we're going to promote in this class. Then we're going to always rely on the paradigm of AlphaZero and TD-Gammon and similar design architectures. Everything is going to be patterned after those, but of course in a much more general framework. Then we're going to rely on visualizations and intuition obtained from Bellman operators and Newton's method, as I mentioned. And through this unification, we will aim to bridge the gap between the cultures of different communities. The AI community and decision control community and the optimization community, they have their own cultures and they are very different, particularly artificial intelligence and decision and control. We're going to try to bridge this gap and bring to bear the power of reinforcement learning to a very broad range of applications, and we're going to discuss quite a few applications. So let me say a few things about the history of the subject. The current state of the art owes a lot to a very fruitful synergy between artificial intelligence ideas and decision and control ideas. Learning through data, learning from experience, simulation, model-free methods, feature-based representations, neural networks, search methods like A*, heuristics. This is the concept that AI has contributed to this mix. Decision and control involves things like dynamic programming, of course, and then things like principal optimality, Markov decision problems, partially observed Markov decision problems, policy iteration algorithm, value iteration algorithms, MPC, optimal control, and so on. These are at the core of the decision and control methodology. And these two fields met sometime in the late 80s and early 90s. And that's how the modern version of reinforcement learning field started. So exact dynamic programming and optimal control go back to the 50s or even before that. Bellman is known as the father of dynamic programming. Shannon is known as the father of information theory and also the father of computer chess, by the way. Now, in the mid-80s, up to the mid-80s, reinforcement learning was a field that, it was a subfield of artificial intelligence that did not seemingly go very far. It was sort of languishing. And then the people who were working on reinforcement learning discovered that a lot of their ideas could be explained and enhanced through decision and control ideas. The first major success was the backgammon program of Tesoro in 1992 and then 1996. Created a lot of enthusiasm for the prospects of this methodology. I personally got involved into this field because I was very impressed by the backgammon programs of Tesoro. Then a lot of people started working in this area. There was progress in algorithms, analysis, mathematical analysis, applications, and the first books on reinforcement learning were published in the mid-90s, mid to late 90s. Then in the 2000s, we had some mega trend developments in technology. Machine learning became very important, found a lot of applications. Lots of data became available, and it was used in applications such as image processing, language translation, and so on. And then we had robotics, which culminated with self-driving cars that you see around in the street these days. Deep neural networks, about 15 years ago or so, became recognized as an important technological development, and they were introduced in systems enhancing applications such as important applications such as image processing, language translation, and others. And then we had AlphaGo and AlphaZero in 2017. And this really showed the way, showed that everything could be put together, deep neural networks, big data, self-training ideas, and to solve very, very difficult problems and in a better way. Finally, we have just recently, large language models, ChatGPT, which opened another frontier again, and who knows how this field, where this field is going. Reinforcement learning is central to all the technological developments, and machine learning deals with inference, inferring parameters, inferring states of systems, and so on. Reinforcement learning is the complement of machine learning. It deals with decision and control. So we have inference and using the inference results to make decisions sequentially. That's how the field shapes. And these are the principal developments that are responsible for the current state of the art. Okay, so where are we now? The approximate dynamic programming reinforcement learning methodology is ambitious and universal. What do we mean by this? Well, let's go back to the roots of the field, which is dynamic programming. One characteristic of dynamic programming is that it applies in principle to a very, very broad range of optimization problems, deterministic problems as well as stochastic problems, combinatorial optimization, discrete problems, and optimal control with infinite states and control spaces. One decision maker or two-player games. On the other hand, exact dynamic programming from the very beginning, it was recognized for its difficulties, implementation difficulties. It's plagued by the curse of dimensionality, by which we mean the exponential explosion of the computational requirements as the dimension of the problem increases. And there's a second curse here, the need for a mathematical model. We need, in order to implement the exact dynamic programming, you need to have equations about how the system, the state of the system evolves, about how the control affects the state of the system, and so on. You need to have probabilistic descriptions of uncertainties in the evolution of the system. All of this is very hard to get. So these were the two principal difficulties that of exact dynamic programming that limited its application in practice, despite the fact that it is very applicable to a very broad range of problems. Now, reinforcement learning overcame the difficulties of exact dynamic programming in two ways: by using approximation, use neural networks and other kinds of architectures to reduce the dimension and address this curse of dimensionality. And the second way is by using simulation in place of a mathematical model. In other words, use a computer model instead of a mathematical model. And that was a big part of what reinforcement learning and artificial intelligence brought to this landscape. So where are we now? We have a broadly applicable methodology that can address a very broad range of challenging problems because the foundations are in exact dynamic programming. And these problems are deterministic, stochastic, dynamic, discrete, continuous, games, and so on. It's very broadly applicable. Just about any kind of optimization problem, including ones that you wouldn't think, like combinatorial problems, can be addressed by reinforcement learning and the kind of algorithms that we're going to discuss. On the other hand, the methodology is not very reliable. There are no methods that are guaranteed to work for all or even most problems. Even if you can prove that a method has guaranteed convergence in practice, in theory, in practice, that may not be true because of the curse of dimensionality, approximations involved, and so on. Okay, so it's not very reliable. On the other hand, there are enough methods to try. There are many different methods that you can try with a reasonable chance of success for each one. And if you can find the right method and you can try the right method, you may be lucky and it may work for you. Now, the objective in our course is to structure the methodology in a way that it can guide the art and delineate the sound ideas to try in a given problem from the crazy ideas of which there is no shortage in the literature. So in other words, we want to understand these methods at some reasonable depth to see for what kind of problems each method is suitable. With this understanding, you will be able, given a method that doesn't work for your problem, see how you can modify it, how you can change it so that it can work. And with knowledge of this theory, you're in a much better position to have success in very challenging problems. Let me also give you, speaking about history, let me also give you a quotation from about 30 years ago. This is a quotation from the preface of the Neural Dynamic Programming book that I wrote with John Bertsekas in 1996. It recounts how we got into this field. A few years ago, it's a long quotation, I'm just summarized. A few years ago, our curiosity was aroused by reports of new methods in reinforcement learning. These methods were aiming to provide effective suboptimal solutions to complex problems of planning and sequential decision-making under uncertainty that for a long time were thought to be intractable. Now, the range of problems that these guys in reinforcement learning were addressing was something beyond our mental framework, which was just completely intractable, and we didn't even consider dynamic programming as a method for solving them. So our first impression was that the new methods were ambitious, overly optimistic, and lacked firm foundation. Yet there were claims of impressive successes and a solid core suggesting that the correct approach was through dynamic programming. Now, John and I understood dynamic programming very well, so we were really intrigued and thought we would take a look. And then 3 years later, after a lot of study, analysis, and experimentation, we believe that our initial impressions were largely correct. This is indeed an ambitious, often ad hoc methodology, but for reasons that we now understand much better, it does have the potential of success with important and challenging problems. In other words, we came to the conclusion that this is indeed a flaky methodology, unreliable, requiring a lot of art together with a theory. On the other hand, there were elements of solidity in this methodology, and if you knew how to deal with it, you could have a good chance of solving important and challenging problems like chess or backgammon. Now, this assessment from 30 years ago holds true still. That's exactly what's happening. This is an unreliable methodology with understanding of the theory, understanding the practice, being able to use the tools, have a big computer, and have some luck, you may be able to solve very, very challenging problems. That's where we are. So let me say a few things about the connections to various fields and what we're trying to do, our aims in this class. Now, this course is research-oriented. It aims to explore the state-of-the-art of the approximate dynamic programming and reinforcement learning methodology at the graduate level. We've had undergraduate students in the past in this class, and some of them did very well, but they have been very few. There's an intersection of a lot of different methodologies. You require the maturity of graduate education to be able to get to it with some reasonable chance of success. What we want to do also is we're not going to cover the entire field, but we're going to focus on some special research topics. Rollout and policy iteration, names that you'll hear again soon, are among those. And the main thing is we want you to get started in research. We want you to provide you with the opportunity to explore research in this area, how your own interests intersect with reinforcement learning. Through a term paper, you may be able to take a first steps along a research direction. or improve on some research that you have already done in your lab. We want very much to help you start with research. And if you do that, we will be very happy and we will think that we have been successful. Now, generally speaking, there have been, from this course in the past, there have been about 4 or 5 research papers, publishable research papers that came out of the course. And in other cases, there have been first steps that led to graduate research. So I hope this happens for you too, and we are ready to help you in this respect. References. Okay, I have a book called Reinforcement Learning Optimal Control. I gave this course first in 2019, and following the course, I wrote this book. Then following the offering in 2020, I published another book that complements this first book and also goes into multi-agent problems, distributed reinforcement learning, and also in more detail on rollout. Then after 2022, I wrote this book, which is a different kind of book. It's short, very intuitive, focuses on visualization. It's relatively easy to understand, and it focuses on the fundamentals, this Newton step view of approximation in value space. It's also available on the internet. You can take a look if this is for you. The main textbook of the course is the second edition. I had a first edition 2023. Second edition was done a few months ago, and it's online, and this is what we're going to be following, except it has more stuff that we are going to be able to follow. Homework is going to be taken from this book. Also, the website, my website that was given the first slide, has a lot of additional material. Slides and videos from the previous offerings of the class, and various supporting research papers, review papers, and so on. So all of this is sufficient as textbook. However, there are also some additional sources that you can consult. I have a 2-volume book on exact dynamic programming, but it also has a lot of material on approximate dynamic programming, so it's relevant. I have also a mathematical book on abstract dynamic programming, dealing with Bellman operators and some of this Newton, the foundations for the Newton step interpret framework for our course. This is also available on the internet. Then there's the 1996 book with John Stiglitz, Neurodynamic Programming. These books are mathematical and inspired from decision and control, decision and control viewpoint. Now, there's another very popular book that by Sutton and Bardow, which first came out in 1998, and then there was a second edition, 2018. It's also online, and it's written from an artificial intelligence point of view. So people whose core roots are in artificial intelligence prefer this book, and you may find it useful as well. Then there are a lot of machine learning books, deep learning books. This is a very popular subject these days. Most of these books are not very useful from my point of view, but there's one that I like, which is by Bishop and Bishop, father and son, wrote this book together. And I find this well written, and I can get a lot out of it, so you may want to consult it. Okay, I mentioned that reinforcement learning and decision and control are very closely connected, and the state of the art of the field now is due to this fruitful synergy between them. On the other hand, there are some difficulties. One has to do with terminology. The terminology in these two fields is very different. So you need to have to be able to go from the one field to the other and know what recognize the terms that are relevant. In reinforcement learning, the tradition is to use maximization of value. In dynamic programming, usually it's minimization of cost, okay? So the reward of a stage in reinforcement learning is the opposite of the cost of a stage in dynamic programming. State value becomes the opposite of state cost. Value function is the synonym of cost function, or closely related to cost function in decision control. All of this is irritating but minor, okay? You have to make a mental switch from a sign switch from positive to negative to pass from one terminology to the other. But there are more serious discrepancies in terminology. In decision and control, people talk about making decisions, the decision maker or the controller. In reinforcement learning, the term used is agent, okay? So that's quite different. If you see agent, it's the same as controller or the software that makes decisions. In decision control, the decision maker chooses decisions. The controller chooses controls. In reinforcement learning, the agent chooses actions, okay? In decision control, we're dealing with making decisions about a dynamic system that evolves over time, in discrete time, or in continuous time, like a discrete time dynamic system, or a system described by a differential equation or a partial differential equation. In reinforcement learning, dynamic systems are called environment. Okay, for a person who comes from decision control, this is hard to stomach. Okay, it's very difficult to accept this term environment. However, if you want to read reinforcement learning literature, you have to be aware of this equivalence. Okay, terminology about methods. In reinforcement learning, you're going to see a lot of talk about learning this, learning that, learning a policy, learning a value function, learning a system. The reinforcement learning is part of the name of reinforcement learning. Now, in a dynamic programming related problem, learning translates to simulation, computer simulation, Monte Carlo simulation. Learning relates to generating samples and learning from the samples, which is called simulation. The term self-learning is very popular, and it's also quite descriptive, or self-play in the context of games, like AlphaZero, learned by playing against itself. Self-learning in decision and control translates to solving a dynamic programming problem using simulation-based policy iteration, simulation learning. And policy iteration deals with this is similar to this self-play idea. In reinforcement learning, there's a distinction between planning and learning. Now, in dynamic programming, planning is connected with solving a problem with a model, a mathematical model. Learning is connected with solving the problem with model-free simulation. Either way, you use a model, but in reinforcement learning, it's called planning if you have a mathematical model, learning if you have a simulation model. So all of this can be a little confusing, but you can get used to it. And your textbook has a lot of other terms also, as a cheat sheet that you can consult as you read various literature. Okay, now there's another very, very annoying discrepancy between reinforcement learning and decision control, and it involves notation. In reinforcement learning, problems are posed as stochastic. That's the starting point for most of the reinforcement learning literature. And central in those are transition probabilities. The notation used in reinforcement learning is S for state. So S and S prime are states in this notation. A is action, And this P of S, A, and S prime is the probability that you're going to end up in state S prime if you start at state S and you apply action A. So these are what we call transition probabilities from state to state influenced by action. Now, this is standard in stochastic problems with finite number of states. Sometimes these are called Markovian decision problems. On the other hand, control theory uses the notation of discrete time systems, discrete time equations, whereby the new state at stage k plus 1, xk, x is the standard symbol in decision control. The new state is obtained as a function of the current state, the control that you apply, u is the symbol for control, and wk, which is stochastic uncertainty, some randomness in the equation. Of course, the problem is deterministic, there is no w, but still we use this dynamic system equation. Now, this is standard in continuous spaces problems because it's more convenient. It's very difficult to provide transition probabilities if you have an infinite number of states. In operations research, both notations are used depending on whether you have a finite state system or continuous space system. And typically, when you have a finite state system, this more compact notation is used. Probability of going from state I to state J under control U. So these are the principal notational systems across fields. The important thing to realize, however, is that all the systems are mathematically equivalent. Everything you can do mathematically with one set of notations, you can do also with a second set of notations. It's just a matter of convenience and mathematical convenience in doing derivations, proofs, mathematical descriptions, and so on. Generally, system equations are cumbersome for finite state problems. Okay, describing this function f is difficult. On the other hand, transition probabilities are cumbersome for deterministic problems and also for continuous spaces problems. Starting with a stochastic notation that involves probabilities makes no sense if your problem is deterministic and has no stochastics. It's just bad. It's just a bad choice of notation. Also, transition probability notation for continuous spaces problems leads to very complicated, very advanced mathematics. It's mathematical stuff that you don't want to go to. So it's much better, more convenient usually, to start with a discrete time equation with the uncertainty encoded in this random disturbance WK. So some notation works well for some problems, but not for other problems, and reversely. So what are we going to do? We're going to use both notational systems depending on the context. When we talk about finite state problems, we're going to be using transition probabilities, usually this type of notation. When we talk about continuous spaces problems, we're going to be using this terminology, but we're going to start from this. And about 75% of the course is going to be done in the system equation notation, and the remaining is going to be done in transition probability notation. Depending on whatever is convenient, we're going to be using the appropriate notation. But remember, these two notations are equivalent, mathematically equivalent. Okay, so it's time to have a break. We'll be doing that in every lecture, a 15-minute break. And we're going to get back. In the meantime, you can do whatever you wish. You may wish to ask questions or to think about the first half of the lecture. And you can bring these questions as soon as we start. And then we'll continue with the deterministic dynamic programming.
Okay, let's get started. So let's start the second half of this lecture, which is a bit more technical. we will talk about exact dynamic programming as it applies to deterministic problems. So we will consider deterministic optimal control problems over a finite horizon, whereby we have a system dynamics which generate a sequence of state over a finite number of steps under the influence of control. So starting from x0, as Professor mentioned earlier, the big portion of the lecture will use the system dynamics kind of notation. So starting from a state x0, we apply a control u0 and move to the next state and so on. At the typical stage, at the state xk, if we apply a control uk, the next state xk plus 1 will be uniquely defined by this equation. So given the xk and uk as input to this function f of fk, the next state xk plus 1 will be uniquely defined by this equation. So there is no other argument of the function fk, which we refer to as the system dynamics or system equation. Therefore, it is a deterministic problem. There is no this random term involved. Note that we don't put some additional restrictions on the nature of the state xk. So the xk can be some continuous quantity, or it can be a discrete quantity. For example, if I would like to apply the theory for autonomous vehicles, so the state xk can involve position of the vehicle, velocity of the vehicle, and so on, and heading angle. So they are all continuous quantities. In a different context, suppose that I would like to use the system, this dynamics equation to describe whether or not a student is paying attention to what I'm talking about at the moment. So the state can be whether or not the student is paying attention or not paying attention. So only two states. So in different contexts, the nature of the state can vary dramatically. And this is one of the principal benefit of, or principal power of dynamic programming theory that we're going to develop later on. That is, it applies to a broad range of problems. In mathematical term, this means the state xk, which lives in some space, and the nature of space can vary from context to context, and the same principle apply. Similarly, the control uk are selected from some set uk of xk, which can also vary from problem to problem, and can also depend in the same problem. It can also depend and vary with xk, so which we call a control constraint set. So this process continues from xk to xk plus 1 and so on. After applying n controls, we reach the state xn and the process terminates. Therefore, the name finite horizon. So starting from x0, if we have a sequence of control, given that the system dynamics is deterministic, a uniquely defined sequence of state will be generated. And to evaluate how good the sequence of state, sequence of control is, we can calculate its cost function, which is given by a different class of functions. This gk we refer to as stage cost, or cost per stage. And so for each xk and uk, we give a function gk, which measures the desirability of applying uk at state xk. Note that the difference here is for the final stage, the function gn is only taking as input xn, so there's no control involved because at this point, the process has terminated. Therefore, for a given initial state and a sequence of control, we can define a function that is function of the initial state and the sequence of control, the cross-bounding cost function. And our goal is to, for every initial state, or for the initial state that we are starting from, we want to find among all the control sequences that fulfill this control constraint set such that its cost function is minimized. So given an initial state, we want to find among all the feasible control sequences, the one that minimize this cost function. So since the control sequence has been minimized, or we choose among all the feasible control sequences, the obtained value is a function of x0 alone. It's not anymore a function of sequence of control. And we refer to this as optimal cost function. And this is the primary object we aim to compute in the context of dynamic programming or exact dynamic programming. In addition, we would also like to find out the sequence of control that attain this minimum, right? So in general, this problem, as I mentioned earlier, the nature of state can vary and so on. But in a special case where it involves finite number of state and finite number of control, this problem can be visualized by a graph. So for each stage, we can list all possible state at that stage. So in the initial stage, stage 0, we list all the possible stage, which is all the possible states, x0, and at stage 1, we list all the possible state at stage x at stage 1, and so on. So all the node corresponds to one state. For states in adjacent stages, we can draw an arc that represents a control where the initial state is xk, and the next state, xk plus 1, satisfy the system dynamics equation. So, and the arc would represent the cross-bounding control. For each arc, we can assign, it has a cost per stage. It has this cost gk of xk and uk, which is the cost of applying the control at xk. In particular, in the terminal stage, for all the xn, we don't need to select any control because the process terminates. To encode the terminal cost, we can introduce an artificial terminal node such that the arc connecting an xn to the terminal node t has this terminal cost gn of xn. So the original deterministic finite horizon optimal control problem becomes computing to optimize the cost of passes where to find the sum of arc costs from the initial states x0 to the artificial terminal node. And if we view the cost of each arc as the length of the arc, then the problem is equivalent to finding the shortest path starting from all the initial states to the artificial terminal node. So it becomes a shortest path problem. And in principle, this equivalence between deterministic finite horizon optimal control problem and the shortest path problem holds, provided that the problem involves finite number of states. And as you may know, the shortest path problem is quite well studied and have a rich literature and a lot of applications and algorithms. At the same time, this particular graph generated by a dynamic programming problem has its unique character. In particular, if we look at this state, x2, and starting from this state, there's no path that's going to lead you back to this state again. This is called a cyclic graph. Because of this special unique character, some dynamic programming algorithm is preferred and perhaps perform better in this context. But nonetheless, it's important to bear in mind the connection between this class of dynamic programming problem and the shortest path problems. Well, I mentioned earlier that the dynamic programming ideas can apply to a broad range of applications and applies to problems with different nature of states and so on. The reason is that it is based on a very simple idea, an idea that applies broadly, but at the same time, very simple and very intuitive as well. It's called the principle of optimality. Suppose that we are considering a finite horizon deterministic optimal control problem and starting from some initial state x0. Let's assume we already obtain an optimal control sequence u0 star and so on, k minus 1 star until un minus 1 star. Oh, by the way, from notation point of view, our notational convention would be that for anything associated with the optimal, we will use the superscript star here. So this is optimal, and this is, so starting from initial state x0, after applying control u0 star and so on, we will reach an intermediate state xk star. Now, let's suppose we are considering a new problem. This new problem have n minus k stages. So the initial stage is here, and the initial state is here. And we will call this tail subproblem corresponds to the state xk star. So what is the optimal control sequence for this tail subproblem? Well, it's the tail portion of the original optimal control sequence starting from uk star. This is the principle of optimality. The tail of an optimal sequence is optimal for the tail subproblem. Why? If we provide a mathematical argument, it will be by contradiction. Suppose we have a different sequence. Suppose that starting from xk star, our optimal control sequence is different from the tail portion of the original optimal control sequence. Then, for the original problem, we can obtain a new solution by picking up the initial portion of the original optimal control sequence and concatenating with this newly discovered optimal sequence for the tail subproblem. Then we're going to get something even better than this sequence. But of course, that is not possible because by assumption, this is already optimal. So that's how we argue and give the mathematical argument for principle of optimality. If again, I use the shortest path example, suppose that during spring break, I'm gonna drive from Tempe to Boston. Let's say the optimal path is through St. Louis. Now, for someone travel from St. Louis to Boston, what is the shortest path? It would simply be the shortest path of my trip that cut the tail portion starting from St. Louis to Boston. That would be the optimal, right? So that's basically the idea of the principle of optimality. Now, this is a mathematical description of the same idea. We will not get into it. So the significance of the principle of optimality is that it tells us for a problem, if we solve a tail subproblem, then the solution of this tail subproblem can be applied to address the original problem. And more specifically, let's assume that at K stage, we want to solve a tail subproblem starting from xk. We can rely on the tail subproblem that starting from xk plus 1 and then going backward in stage. Eventually, we're going to get to the tail subproblem starting for initial state x0, which is the original problem we aim to solve. And at that point, we will solve the original problem. In particular, let's assume that we want to solve this tail subproblem corresponds to xk. And we will call the corresponding optimal cost as optimal cost to go and denoted by jk star of xk. Suppose further that we have already solved all the tail subproblems starting from any state xk plus 1. Now, to solve the tail subproblem starting from xk, for the original problem, if we try to use brute force, we need to consider all the control sequences uk, uk plus 1, and so on, right? But principle of optimality tells us that starting from some uk prime, let's assume this uk prime is the optimal. Then the tail portion of the tail subproblem, we already computed and obtained the solution. So by concatenating this uk prime with the remaining optimal control sequence, we immediately get the optimal control sequence for this tail subproblem. As a result, instead of considering all the control sequences starting from xk, we only need to consider the available control options at k stage and concatenating the remaining and compare those options. That is to say, consider every possible uk and solve, given that we have solved the tail subproblem that starts from next state xk plus 1. And this, by doing so, we obtain an evaluation of how desirable each control is and select the one that gives the best result. Note that during this process, I need to solve all the tail subproblems, not some tail subproblems. I need to solve all the tail subproblems because in order to solve the tail subproblem of xk, I rely on the values of optimal cost to go at k plus 1 stage of all possible k plus 1 stage. So this is very important. And that is to say, the idea of dynamic programming algorithm is solve all the tail subproblems of a given time length using the solution of all the tail subproblems of shorter time lengths. More specifically, it produces the optimal cost to go, jk star of xk, of the xk tail subproblems by starting with k equal to n, in which case the optimal cost jn star of xn is already given. So there's no, we only simply set it to the terminal cost Gn of Xn for all Xn. Then going backward in stage, starting with n minus 1, by this formula, we compute Jn minus 1 star of Xn minus 1 for all possible X at n minus 1 stage and move backward in stages. Eventually, we get J0 star of X0, and the optimal cost J star of X0 is simply equal to J0 star of X0. Anyone have questions, or is clear? Okay. So getting back to the finite state problem, starting with the last stage, we set for all Xn, Jn star of Xn equal to Gn Xn for all X. And then going backward to Jn minus 1 star and so on by using this formula. Again, for each UK, this expression provides a desirability of applying UK. So this is an immediate measure of desirability. And this part provides a long-term measure of how desirable of applying UK. And we minimize among all possible UK and to get the optimal. So we're going backward in time, backward in stages until we reach the stage 0 and get J0 star of X0. So we call this first phase of computing JK star, the optimal cost to go. Now, suppose we are solving a very large scale problem. The total number of states can be zillions. Then you need tremendous storage to store all the numbers, J star, the optimal cost to go. Note also that while computing this minimization, you may as well also store the control that attain this minimum. But the problem is, if there is tremendous number of states, zillions of states, then simultaneously, if you compute those UK star, you need zillions of control to be stored. So the storage effectively would be double. But of course, there are ways to reduce and, okay, let's not get into that. Well, alternatively, suppose that you have gone through the backward in stage calculation and compute all the optimal cost to go, Jn star and so on, and have them stored in your computer. A different way to construct the optimal control sequence is, again, starting from the beginning and going forward by, suppose at the current state X0, you calculate U0 star by this equation. It's the same equation, except that now you focusing on looking for what is the control that attain the minimum. And after applying U0 star, the system gonna go to X1 star by this formula, and sequentially going forward, as we reach XK star, we apply this control. Okay, what is the advantage of this approach? We will refer later on this kind of calculation as online play, as opposed to the previous backward in stage calculation, we call it offline training. So we call it online play. So can there be any benefit of this approach? Basically, in this way, as you can see in this figure, well, the operation already starts, right? We are at x0. We already know we are at x0. We don't need to control compute the control for all the other state at 0 stage, which is irrelevant to us. We only control the U0 star that applies to x0. And we move forward to x1 star, and we calculate again this equation by looking for this U1 star. We don't need to calculate the optimal control corresponds to applies to other state in this stage. So we calculate the control as we need. So, and more importantly, in the context of approximate dynamic programming, this is typically how we calculate control, because one of the problem is the state space is enormous. To store all the controls would be typically infeasible. And yeah. Okay. Now let's get into some examples. Well, first consider a discrete state deterministic scheduling problem, whereby we want to find optimal sequence of operations A, B, C, and D. We impose constraints that operation A must precede B, and C must precede D. One of the challenging exact dynamic programming is the modeling phase. So although dynamic programming is a very powerful tool and so on, but it can be a little bit challenging and need a little bit of creativity to model a problem at hand into the dynamic programming formulation. So how can we do that? For the stage 0, we just introduce an empty state, which means we haven't arranged any operation. We haven't scheduled any operation. So any state will be a partial scheduling. So starting with the initial state, stage 1 involves the states that has scheduled one operation. So stage 2 involves all the states after have 2 operations scheduled. And the stage 4 involve partial scheduling with 3 operations, and we don't need any further because the last operation is implicitly defined at this point. There's no control anymore. And we have the cost marked along the line. So note that in this graph, the control constraints that A must precede B and C must precede D has already been incorporated, because starting from AB, the only feasible control is to apply scheduling operation C, because if we schedule D, then it would violate the constraint that C must precede D. Now we recall that the dynamic programming idea is to break down the problem into smaller pieces. So starting from the last stage, we solve the tail subproblem involving only one stage, and we move backward in stage and solve this problem involving 2 stages, and so on. Okay. So for the tail subproblem involving only the last stage, we already have the problem solved by setting the optimal cost to go simply equal to the terminal cost. Now for the problem involving 2 stages, let's say consider the optimal cost to go starting from this partial schedule CA. We have 2 options. One is to schedule B, which this part of operation costs 2, And after we reach CAB, this partial schedule, only D remaining, and applying schedule D after B would cost 1. So the total cost would be 2 plus 1. And similarly for this one, the terminal cost is 3, and optimal cost to go starting from here is 3, and schedule D after A cost 4. So 4 plus 3 is 7. And we just compare those two numbers, and the optimal cost to go apparently is 3 because 3 is smaller than 7. So for all states at stage 2, we need to repeat this procedure involving 2 states. We need to repeat this procedure and calculate their optimal cost to go. Now we move backward in stages. For this stage, starting from a partial schedule C, we can schedule A after C or D after C. Now, having computed optimal cost to go for CA, which is 3, schedule A after C, the corresponding term we need to evaluate is 4 plus 3, whereas schedule D after C costs 6, and the subsequent optimal cost to go is 5. So we compare 7 and 11, and we find out 7 is better. So, and similarly, we need to do similar calculation for A, and this is the value we obtained. Now, having calculated the optimal cost to go for A and C, we can go back to the initial state, which is the empty schedule. And we consider 2 options, C or A. Schedule A would cost 5, and then the subsequent optimal cost to go is 8, then it's 13, whereas schedule C is 3, and subsequent optimal cost to go is 7. So this one is smaller, therefore the value is 10. At this point, the stage 0 subproblem is the entire problem. And the optimal value of stage 0 subproblem is the optimal cost. Note that in the previous calculation, while I was calculating the optimal cost to go, I can simultaneously also record the subsequent schedule, right? For example, while I was calculating here, I can simultaneously, next to this number 3, I can also mark, like record B is better, right? And similarly here, while I was calculating 7, I can also simultaneously record, at this point, I should choose A, so put an A here. But we can also, after constructing all the optimal cost to go, we can move forward and reconstruct this optimal scheduling. Let's briefly talk about another discrete optimization problem, which is kind of a scheduling problem, but very famous, traveling salesman problem, whereby starting from an initial city, our goal is to traverse all the cities once and once only, and go back to the same city. And in this particular example, we start from the city A, and we want to traverse all the remaining cities once and once only, and move back to the same initial city. So in this case, we don't really need to introduce this artificial initial state, because we already know the initial state is A, the initial city. And we use this matrix of intercity cost to represent the cost between traveling between different cities. So along this row is the distance between A to B and A to C and A to D. and so on. And you can see this matrix is symmetric, and this will be referred to in literature, often referred to symmetric traveling salesman problem. And in some other cases, the cost may not be symmetric. For example, A traveling to B, the cost is different from B traveling to A. But nonetheless, it does not affect the effectiveness of our dynamic programming algorithm. So starting from the state at the last stage would be the complete tour before going back to the initial starting city A. So this is all the possible states at the last stage. And as you can see, this state, its cost would be the cost traveling between D to A, which is 15, as you can see here. And similarly, the cost between from the terminal cost of A, B, D, C would be 1, because traveling from C, city C to A cost 1. So this is already given by this matrix of intercity travel cost. We will move back in stage and consider all the states that is composed of 3 cities. All the tours, partial tours, involve 3 cities. So at this point, we don't really have a choice. So there is only one control. And we solve the problem of this stage, and we move back. And at the partial tour AB, we can go to C or go to D. And the optimal cost to go of ABC is 18, whereas the optimal cost to go of ABD is 4. Now, to evaluate this choice and this choice, we just need to compute the sum of this arc plus this optimal cost to go. So from B to C, cost 20, which is marked here. And the optimal cost to go of ABC is 18. So this choice, we get 38, whereas this choice cost 8. So we mark 8 here. We write down 8 here. And similarly for AC and AD. Now we go back to the initial stage, and we are solving the original problem. And note that in this particular example, we get 2 optimal control sequences. And it is allowed, and it can happen in practical problem, and it doesn't affect the effectiveness of dynamic programming. So dynamic programming allows this case where you can have multiple optimal solutions and so on. Okay. Another example, which is the next word prediction. Oh, it has a connection with this model called N-gram, and dating back to the 40s, where Shannon developed this model. Although, of course, Shannon would not be able to predict how this model can, how far this model can go. And definitely, my judgment is he would not expect that how capable this model can be with trillions of parameters and so on. So we can use this model to describe the text generation process of some given large language model, whereby the states xk is the n-word string given the current text window. And the control that we would like to select is the next word. So given the current text string, we select the next word and we put the next word in the front of the text string and remove the word at the end of the text string. So this is a deterministic system. And we move on to the next state, xk plus 1, and choose the new word and so on. So at this point, it has nothing to do with dynamic programming yet. Suppose that we are given some cost function, the terminal cost. We have some evaluation criteria. We have some criteria that judge the quality of the text string generated after n stages. So this would be the cost. And well, the intermediate text strings have 0 cost. So we don't evaluate the previous stage text strings. At this point, we obtain a dynamic programming problem that has only the terminal cost and no intermediate cost. And we would like to select the control sequence such that it's optimal measured by this cost function. A trained neural network or GPT can generate such text strings. So given the initial state x0, it will generate a state control sequence x0, u0, and so on until xn. But is it optimal with respect to the cost function we measure here? We don't know. And quite often it's suboptimal. So a GPT can be viewed as a heuristic or suboptimal control generation method, which we will call policy or base heuristic in the next lecture. Now, the x0 can play an important role in the quality of the text we generated in the end. This, in the context of large language models, typically referred to as prompt. And by designing the prompt, you can potentially get a much better result. And the art of designing the prompt is often referred to as prompt engineering. It's a completely quite active area of research, and it has a challenge of its own. Okay, given that we have modeled this problem as a dynamic programming problem, so in principle, it can be solved by exact dynamic programming, but only in principle. The reason is the state space is enormous. It's gigantic. So all the possible words here in the context of large language model typically referred to as tokens, and it has tens of thousands of tokens, and the size of text window is growing tremendously. So all the possible combination of text string is too big to compute or to store in your computer or in any computer. So it's totally intractable. On the other hand, the concept of dynamic programming theory apply and can form the basis of approximations. As we will see later on in one of our application lecture, we will apply the methodology developed in this course to generate most likely sequence, in which case the cost function Gn is the probability how likely a sequence is measured by a language model. Okay. As I mentioned earlier, the nature of the state can vary from problem to problem, while at the same time, our principle applies. So the case where the problem involves continuous states is its research typically is in the field of classical control theory. And the control theory has a long history, more than a century, have wide range of applications. The heydays of optimal control is during the time of 60s when during the space race and space exploration, and the control theory contribute tremendously to its success. Yeah. It always had a significant role in the chemical process industry. More recently, the control theory applied widely in robotics application, in self-driving cars, and even in healthcare application, as we will demonstrate in one lecture. So the control problems addressed are widely can come in a diverse variety, and generally can be categorized in two types. One is referred to as regulation problem, where our goal is to make sure that the state stay close to some set point. For example, for temperature control of the building, once you set the temperature to be 73 degrees, you don't want it to fluctuate from 50 to 90. You want it to stay close to 73. Despite the changing of the environment, whether or not the outside is raining or is sunny during summertime and so on, or always sunny during summertime. An academic example of this problem is carpool example, where you have a mass on top of the bar, and the goal is to push or pull this card such that this bar keeps vertical. So in this case, the state is the angle theta of the bar between the bar and the vertical line and its derivative. The other class of problem is the planning problem, where instead of trying to keep the state stay close to some predefined set point, you would like to compute a path from a state A to state B. And there are various constraints imposed on this problem, like the velocity constraint, position constraint, you would like your car to stay on the road, and there are some fixed obstacles, and there are some moving obstacles like the surrounding vehicles and so on. And given that you don't have complete information of how the neighboring car gonna maneuver in the following 10 seconds, it may maneuver aggressive than you have anticipated. As a result, you may need to replan your path. So it need for online replanning. At the same time, there is tight online computational budget constraint. It comes in two ways. As an autonomous vehicle, for example, there are a lot of information you need to process. You have a lot of cameras, LiDAR, and so on you need to process. And the passenger may want to enjoy some videos. So there are restrictive computational budget. At the same time, it's not like playing games. You can pause the video or pause the game and just think about it. How can I pass? How can I plan for the following 10 seconds? The robot need to calculate a new path in a split of second. Otherwise, the driver behind you is gonna get angry. So there is also tight constraint on the computational time. Due to the limitation of computational budget, the time and complexity of the problem, approximation are essential. And in this field, in this application area, MPC type of algorithm can be quite useful. While talking about approximation, let's give a high-level overview of approximate dynamic programming algorithm, which connects to reinforcement learning algorithm. Recall that the exact DP algorithm for the optimal control generation starts with calculating U0 star by finding the minimizing control U0, minimizing control. And then the system state gonna go to X1 star, and then moving sequentially going forward, we can compute UK star online. Now, in the previous slides, we call this phase 2 process to construct the optimal control sequence, right? It is phase 2 because in phase 1, we already compute J stars, the optimal cost to goes, right? J1 star, J2 star, and so on. What if we cannot compute J1 star, J2 star, or the optimal cost to go, either because the problem is too complicated or there are too many states involved, and so on? Well, if we can use some method, any method, that computes some JK tilde, which we assume carries some information of JK star, which this approximation we denote as JK tilde. And this process, we will call it offline training. Through offline training, we obtained some JK tilde. Then we can obtain a sequence of suboptimal control by placing JK tilde in place of JK star. So starting from X0, we calculate U0's tilde by minimizing this equation and move sequentially going forward. And this calculation, this process calculating U tilde at different stages is called online play. Now, what is the rationale of this method? Suppose our UK tilde carries a lot of information of JK star. In the extreme case, let's assume that UK tilde is simply JK star plus a constant, 1,000,000. What control sequence we're gonna get? U tilde. How good is this U tilde? If our JK tilde is J star plus 1,000,000. Yes, please. Yeah, it's exactly the same. Because this constant doesn't affect the control selection. So what really matters is if we can compute some JK tilde that carries the information, useful information of J star, it can be used to guide our control selection process. And this is a key idea that we're gonna go back many times. Okay, at this point, anyone have some questions? All right. So starting from deterministic dynamic programming, or exact dynamic programming applies to deterministic optimal control with finite horizon, we're gonna move forward to consider stochastic finite horizon problem, whereby the state xk plus 1 is also affected by a random parameter in addition to xk and uk, which means at state xk, after applying uk, we don't know exactly what the state xk plus 1 is, because there is some random quantity involved that's going to affect the transition to the next state. As a result, it is not equivalent to shortest path problem. It's more difficult because of this randomness involved. We will also consider infinite horizon problems, whereby instead of having n stages and after that the process terminate, the control selection process and state control sequence extend indefinitely. As you may expect, the dynamic programming theory for this infinite horizon problem is more challenging, but at the same time is more elegant. And the reason is, let's say at stage K, we are at some particular state X. And that problem is exactly the same as we are at stage k plus 1 and at the same state, because we are facing the exact same problem. It's an infinite horizon, and as a result, we don't need to compute optimal cost to go for different stages. Rather, we will only need one optimal cost. We will also consider stochastic partial state information problems. What is partial state information? Up until now, we only consider the case where I said that we have access to this information xk, and based on xk, we calculate control. Now let's get back to this example that I'm trying to figure out a particular student, whether or not the student is paying attention to what I'm talking about, or is already thinking about what to have for dinner. And based on this, I'm gonna perhaps talk about a joke to attract attention. Now, I'm not a mind reader, and nor the student gonna tell me what is going on in his or her mind. I can only observe his or her expression, this person's expression. And based on this expression, I can have a guess or a belief of the state. And based on this belief, I will make the decision. And this is what we are saying here. We will convert this problem, the partial state information problem, to a perfect state information problem, whereby the state is not anymore the internal state of that student, which I don't have access to, but rather my belief based on my observation. And then we can apply exactly the same dynamic programming principle. Not quite as simple though, because for the previous problem, if you know the student's minds, there are two situations, either paying attention or not paying attention. Whereas now, if convert to this perfect state information problem is my belief. And belief can be 10% the student is paying attention or 50% paying attention and so on. So it becomes a continuous quantity and become much, much more challenging than the previous one and can be hard to solve even approximately. But there are a lot of applications that fall into this category, and we will see later on, particularly in one of our applications, that some of our method can be applied with success. We will also consider minimax and game problems. The exact game DP theory for this class of problems are substantially more complex. But the most spectacular successes in recent years of reinforcement learning involve games. We will discuss RL method and in the context of computer chess, and we will showcase that how the method developed here can apply. Let's talk about some organizational issues. The aim of our course is to help you think about how reinforcement learning methods, particularly the methods covered in our course, can be applied to your research interests. So for this reason, we have de-emphasized some complex mathematical issues involved in the dynamic programming and reinforcement learning theory, because we want to help you to connect your research with the methodology introduced here. At the same time, we want to emphasize that there are plenty of math that is involved in the dynamic programming and reinforcement learning theory. And for those of you who are theoretically oriented, there are no short of analysis that one can do. For this course, we will have 3 to 4 homeworks, and the total homework counts 30%. And at the later phase of the course, the student will, all of you will be encouraged to choose between one of the two options, and you will be encouraged to try a mini research project where you can team up to 3 persons to do a research, and based on the methodology introduced in this course or some other closely relevant methods apply to your research of interest. And in the end, we will select a few successful applications for presentation. However, if you feel that's too much a task for you, or if you cannot proceed after an initial try with this mini research project, you can choose to do a read and report term paper where you cannot team up. You need to do this alone. And you choose 2 to 3 research publications and provide a synthesis. What do I mean by that? I mean, we do not expect you to provide a summary of this paper, summary of the second paper, and the third paper. No, we would like you to point out the connections, the similarities and differences between those two or three papers, the methods introduced in those 2 or 3 papers, and their connections with the course material covered here, and how it can be viewed conceptually, and what is the potential for their modification, and what are pros and cons for those methods introduced in those papers, and compare them with the method introduced in our course. So, of course, we will very much pay attention to how close the synthesis, the report is to any of those generated by any of those models you know. So the attendance in person is a requirement. Of course, assume you are not ill. And we hope that being present is also helpful for your learning experience. For notation, as mentioned earlier, there are we aim to cover a broad range of applications coming from different domains, and there are different notations used for people in different areas, AI/RL, control theory, operation research, and they focus on different problems and use different notations. And the AI/RL and OR people focus on discrete and finite state problems, and which are stochastic, often is Markovian decision problems, and using transition probability notation to describe uncertainty, whereas control theorists use the system equation notation, and this set is well suited for continuous state and problems and deterministic problems. We would really appreciate if you can make an effort to use the notation that has been used in the lecture notes or in the slides or in the textbook, because it makes it easy for us to understand what you have done and helps us to get our idea better, and also help our communication if we will discuss further. So it helps make it life easier for us to help. Okay, as I mentioned earlier, that we have made an effort to focusing on helping you applying the method introduced here for your research project. For this reason, we have de-emphasized to some extent the mathematical aspect of the theory. As a result, the math requirement for this course is simple and modest. Only calculus, elementary probability, minimum use of vector matrix algebra. And in fact, we made an effort to avoid vector matrix algebra. So pretty much they rarely appear in the material. Our objective is to use math to the extent that needed to develop insight into the mechanism of various methods and to be able to start research. On the other hand, it is tremendously important in our view that a mathematical framework is developed in your mind, because it will help you to delineate, to find out what is a sound approach and what is a flaky approach. And it will help you to model the problem and understand the solution. And dynamic programming relies on substantial mathematical theory, especially for infinite horizon problems. As a result, there is no short of analytical research that can be carried out. So for those of you who are theoretically oriented, there can also be plenty to do. So let's go quickly through the syllabus. In the subsequent, or in this course, we will cover some algorithmic topics, including introduction to exact and approximate dynamic programming, approximation in value space, and briefly in policy space, offline training, online play, and their connection to Newton's method. And we will focus, a big portion of the course will focus on rollout and approximate policy iteration, as well as some prominent control methodology, model predict control. I did not mention adaptive control. This means that the control selection process adapts to a changing environment. We will also touch upon multi-agent problem, where there are multiple robots or multiple agents involved, and it has its unique challenge. We'll introduce a method tailored for it. And we will talk about discrete optimization using rollout method, sequential estimation and Bayesian optimization, as well as training of feature-based approximation architectures and neural networks. On the application side, we will talk about robotics and autonomous systems in multi-agent environment, application to large language models using the n-gram formulation we introduced earlier. We will apply, consider the inference and optimization of hidden Markov models, data association problems, two-person games and computer chess, infrastructure network and supply chain, cybersecurity application, where we would like to figure out whether or not a network system has been intruded by some invaders and so on, as well as healthcare applications. Okay, homework. The first homework we'll do in 1 week, and it's a very simple one. And exercise 1.1a of the textbook, only the part A is needed. You can type it out and you can write it down and scan it and submit in Canvas. The overall structure of the lectures is that the first 4 lectures will aim to provide an introduction and overview of the subject in our view, which will facilitate selecting and focusing on some research area. And so after the first 4 lectures, we will have a rough idea of what we aim to cover. And starting from that point on, you can start think about what you want to do for your research project or do a synthesis of some research articles. The remaining lectures will develop the topic listed above in greater depth. So each lecture we will focus on a particular method and or introduce some successful applications. In the second lecture, we will cover the dynamic programming algorithm for stochastic problems, as well as the corresponding approximation in value space. So the textbook is online, and please read as much of the textbook as you can. And there are a lot of materials online, including the previous video lectures, slides, and so on. It's all listed here. Okay, with that, thank you so much for your attendance. See you next week.